Dear students, today in this particular lecture, we are going to discuss about torque acting on a current loop and preliminary things about galvanometer. So here we go. First of all, let us start torque acting on a current loop. To study torque acting on a current loop, what we need is that the diagram, and definitely we need a loop also. So here I have not written the things in detail. You can see the notes where the details are there, but in this one I am going to explain how the expression of torque acting on a current loop arrives. For this, you should know that in your class 12 you had an expression that force experienced by current carrying conductor is equal to current and factor product of the length and the corresponding magnetic field. So this formula is going to be used here to find force on the arms of the loop. So let us move on. So we'll concentrate in the diagram here. In this diagram you have a rectangular loop. There is a uniform magnetic field shown by B, and the loop, its name is PQRS. The loop arm RS and QP, they have length L, and the other arm SP and RQ each have length equal to B. So, and here we have one single turn only. Again, I would like to tell you is that here there should be an arrangement of entering the current, but here in this diagram I have not drawn that, because you will see that it is a closed loop and there is no way of entering current, but for the sake of simplicity I did not draw. This rectangular loop is also capable of having a rotation about this axis, which is shown by the dotted line. Now let us try to analyze different forces which are coming in the loop due to the magnetic field and the current flowing through it. So as you see in the diagram, we have a current I flowing in plane of view. Okay, so we have this diagram, and with this diagram we are going to analyze the forces in the different arms. So I have called the SP arm as arm 1, then PQ is your arm 2, QR is your arm 3, and RS is your arm number 4. For simplicity, we have given names to the arms so that you can easily understand. Now let us try to go and analyze forces in each arm. So first we'll start with that SP arm, arm number 1. For convenience, I'm denoting the force acting on the arm SP of the loop as F1. So let us try and see. Before that, I would like to tell you is that the loop is placed in such a way in the magnetic field that the normal, which I have shown by letter N, is making an angle theta with the direction of magnetic field. This particular derivation is done with normal to the plane, making an angle theta with the direction of magnetic field. However, in different books, you will find that the coil itself makes an angle theta with the direction of magnetic field. But here it is not that way. In my case, the QR, that is the direction of current, is making an angle 90 minus theta with the magnetic field. That is, the coil makes an angle 90 minus theta with the direction of your magnetic field. So going back to the arm SP, in arm SP, I will show you that this is the magnetic field B and this is your direction of normal, and the direction of advancing current is in the direction of SP. So this SP will give you the direction of the length vector. You know the formula, you have F equals to I L cross B. F equals to I L cross V. This is the formula. F is like this, vector F equals to I L cross B. L vector, length vector, cross B vector. So here we have the force, how here we have the current and the magnetic field direction here. So our expression for force is F1 in vector notation equals to I, which is the current, and instead of L here we have B, because the side SP is equal to B. So I have written it as B vector cross that capital B. Capital B is your magnetic field. So you will see that the angle between this small b, that is the direction of current, corresponds to that small b here, and capital B is this 90 plus theta, that is 90 plus theta. And the cross product you can easily realize by applying rule of cross product that this is your B vector, this one is your B vector, and this is your capital B, and the cross product will go like this: B2, small b2, capital B. You will rotate the screw and it will go down here. So the force will be directed perpendicular to that SP arm but along this dotted line, and its value will be what? Let us see. Its value in magnitude will be IBB sine 90 plus theta. Sine 90 plus theta is cos theta. So the expression for force 1 will be I small b capital B cos theta. Next, let us try to go to the arm RQ. I did not go to the arm PQ, we'll come to PQ again, but let us go to the arm RQ, or you can say QR. Current flows in the direction of Q to R, and here we have given the force a name F3. Why F3? Because it is arm number 3. So in this case you will try to find out the expression for force. This time it will be F3, and what will be its expression? It will be capital I small b cross capital B. Why small b cross capital B? Small b is the length of QR arm, and this is the length L vector here, B vector, multiplied by capital B. What is the angle between small b and capital B? Small b vector is directed along the direction of current here, and this capital B is here. Between them, this is the angle 90 minus theta. So magnitude of F3 will be capital I small b capital B sine 90 minus theta, and your cross product will go from this to this, that is screw will turn from capital B to small uh, screw will turn from this way. It will turn from small b to capital B, in anti-clockwise direction here, and as a result force F3 will have direction perpendicular to this arm QR, but it will be directed along this axis. This frame is capable of rotation about this dotted axis, and F3 will be directed upwards. You will see an interesting thing now, that this F3 and this F1 are directed along the same line, dotted line, and their values. What is the value of F3? F3 is IBV cos theta, sin 90 minus theta is cos theta. So their magnitudes are equal, but their directions are opposite, meaning that these two forces would cancel, and so there will be no force in the direction of this axis. So I hope this is clear here. Next, let us now go to the arms PQ and RS. If you go to the arm PQ, then it is very simple here. You have this direction of your L vector in that formula, F equals to IL cross B, and this is your magnetic field vector, which is very much clear that the direction of L vector and B vector are at right angles to each other, so their cross product will be in this direction. So that will be your F2. And in the case of your RS, again this will be the direction of your L vector, and this will be direction of your magnetic field B. The angle between them will be 90°, and if you take cross product, your cross product will go, this screw will turn from this to this, and the F4 vector will be directed upwards towards us from your computer screen here. But what are their values? We have seen that F2 will be directed this way by rule of cross product, and F4 will be directed this way by the rule of cross product. But what will be their values? So their values I'm going to show you now. Yes, here you will see that the value is simple. F2 equals to IL cross B. Here the length is L here for the arm PQ as well as RS. So F2 in magnitude will be ILB sine 90. Between L and B you have 90° angle as depicted in the figure itself. So F2 will be ILB sine 90°, and your F4 will also be having same value. Now if you go in detail and try to analyze the forces coming on the arms PQ and RS, then now after taking the cancellation effect of F1 and F3, you have this diagram. This picture shows you the F2 at Q. This is your top view. You have QR arm is shown from top view. We are showing you a top view, and from this top view at Q the force F2 acts like this, and at R the force F4 acts like this. For a little comparison, this vector should have been of same size, but in my case F2 is appearing to be a little larger than F4. Anyways, I will remind you that F2 and F4, if drawn nicely, you should have those two vectors drawn with same size because their values are same. Anyways, coming back to this diagram, you will see that I am producing Q and R backwards, and they meet at capital M, and the direction of magnetic field is making an angle theta with the direction of normal always mentioned there. Now if this angle is theta, then this particular angle is 90 minus theta, which I am showing by marker now, and so this angle will also be 90 minus theta from geometry. So you have a right angle triangle QMR with this angle QRM being 90 minus theta. Now what is torque acting here? Now these two forces F2 and F4, they are acting at 2 points Q and R. Their magnitude is same, but they are not acting at the same point, like, or not acting through same line. Your F1 and F3, they were acting along the same direction, so they cancel. But here it acts at Q and here it acts at R, so they will not cancel. Rather, because they have a distance of separation Rm, this direction of F2 and direction of F4, they have a distance of separation Mr, so they will constitute a torque here. Two unlike parallel forces separated by distance, they constitute a torque as per definition of torque. So you will see here the expression for torque is either force, that is F2 or F4, multiplied by the perpendicular distance between them. This I am not going to explain here. This is already there in class 11 itself. Torque is equal to one of the forces multiplied by the perpendicular distance in magnitude. I have not written this in the vector form yet. We will wait for that. Now torque will be F2 and F4. So F2 or F4, their value is ILB multiplied by Mr. Mr is the perpendicular distance of line of action of F2 and thus F4. So Mr can be written as QR cos 90 minus theta, because your Mr is your base and QR is hypotenuse of that triangle QMR with respect to the angle R. So you will see that here tau is ILB QR cos 90 minus theta. So torque tau is equal to this QR now replaces by the value B. QR is your B here, and your length and breadth multiplication gives you area. So area is equal to length into breadth. So A is the symbol here. So your torque expression is capital I, capital A, capital B, sine theta. Cos 90 minus theta is sine theta. So that is for your expression of torque for a single loop of one turn put in a magnetic field such that it's normal to the coil, makes an angle theta with the direction of magnetic field. Tau equals to IAB sine theta. Now suppose you have capital N number of turns in your loop. So then the torque will be additive, that is each loop will add to the torque and net torque will be NIAB sine theta. So this is the expression for torque for n number of turns in the loop. Now we define a new quantity called magnetic dipole moment. Magnetic dipole moment is a quantity which is the product of current into area of the loop. So if n turns are there, then the total current is capital N into I, this multiplied by area. So this is called magnetic dipole moment of a current loop. You will study magnetic dipole moment in that magnetism units of the same paper. So I am not going to details of magnetic dipole moment here. But now you see, in context of this magnetic dipole moment being NIA, so that NIA is equal to mu. Go back and see here you have that tau expression NIAB sine theta, so that NIA, this product is replaced by mu. So on replacing, you are getting tau equals to mu b sine theta, and in vector form I can write tau equals to mu cross B. How can I write tau equals to mu cross B? So here the magnetic dipole moment, its direction also comes into picture. What is the direction of magnetic dipole moment? Direction of magnetic dipole moment is always perpendicular to the loop which you consider. For example, when you consider this loop, in this loop my direction of current was like this, these, 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 and this. So here the direction was like this way. If you see from this side and from that side, it will be the other way. So here you will see that your magnetic dipole moment will be in this direction. That is your direction of your area vector. So area vector, if suppose we have a loop like this and my direction of current is this way, then the area vector will be this direction. In this direction my area vector will be in this direction. Okay, so for that your magnetic dipole moment will be in that direction outward, and here because the direction is this, this, and this, so your expected direction of mu is that way, and your B direction is this way. So this angle between mu and B is theta, just like the area vector. So your torque is mu cross B, because mu cross B, magnitude of mu cross B comes out to be mu B sine theta. So this is the expression for torque in terms of magnetic dipole moment. The expression for magnetic dipole moment is quite not necessary here, but still we try to give you this, and from this expression it is very much clear that whenever we put a loop in a magnetic field, it will give you a torque if you run a current through it. Then what is the application of this? What are the applications, possible applications? So one of the possible application of a loop getting torque while put in a magnetic field is in galvanometer. Which type of galvanometer? It will be moving coil type galvanometer. So the basic principle of a moving coil galvanometer is that you have a coil like this one. This coil, once you put it in a magnetic field and send a current through it, it will get deflected. Okay, fine, there will be a deflection. Now the question is that deflection enough to give you a galvanometer? That is, you have a magnetic field, you have a coil, and you run a current through that coil, and as per this expression, torque will come and there will be deflection. The answer is no. Only by placing the coil in the magnetic field and sending a current will not give you action of galvanometer, because you have seen that in a galvanometer in your laboratory, generally which you call as Weston type galvanometer, you have a pointer and the pointer swings just like a pointer swings just as when you put a current and you get a deflection proportional to current. So we need to do something more in order to get a galvanometer from this principle. How? Let us see and go there. So you will see that this is the picture. Here you have a coil, and this coil is of several turns, and this coil of several turns is there wound over a frame. That frame will be as per necessity. Generally this will be over a aluminium frame, maybe in Weston type galvanometer, and the other end of the coil will be connected to a hairspring, and the hairspring is again connected to a pointer. Now what is the role provided by this hairspring? I am coming to that, but before that you will see that you have one system of pole pieces of two magnets, and the arrangement is interesting. That is, they are cut in a circular groove so that the magnetic field becomes radial. How and why this is done? This is done so that your magnetic field acquires this shape, this. So what is the usefulness of this arrangement? You will see that the field lines are getting stronger and stronger, so the deflection will be better, and everywhere the direction of that area vector, I'll show you by diagram, direction of this area vector A, and the magnetic field will be 90-degree. That is one another thing that will come in this case. So coming back to that diagram, you will see that here the pointer is put over that hairspring. Now coming back to that hairspring, why this hairspring is connected? So this hairspring is connected to this coil so that it can give you a counter torque. Whenever a current is sent through this system, the coil will experience a deflecting torque, and initially the deflecting torque will be there, but there will be a restoring torque provided by the hairspring as the spring is twisted by the deflecting torque, and the spring will tend to produce a counter torque, and that counter torque, which we call as restoring torque, will be exactly balanced after a little while with the deflecting torque, and you will get a steady deflection in the galvanometer system. So this is the way we make a galvanometer. Let me show you the expression also. As I told you that your torque will be NIAB, which we already have found out, and this is the expression. Phi is the deflection produced, and C is your torsional constant. Here it is a mistake. C is the torsional constant of the spring, and torsional constant is defined as the restoring torque per unit twist, and the deflection phi is indicated on the scale by the pointer. So phi into C, that expression is for the counter torque. NIAB is your applied torque, and when you equate, you get phi equals to NAB by C into I. That is, more is the current, more is the deflection. Again, when I tried to show you, I did not try to mention over what material this coil is wound over. Here the coil would be wound over as per the requirement, maybe conducting frame, maybe non-conducting frame. But you will see this diagram this side, and it will be much better here once we show you the next diagram. Here in this diagram you will see the current direction is shown and current return direction is also there. Here spring is also shown, and you will see that how is the winding here and how the pointer is connected to that hair spring arrangement. And this is your galvanometer which you see in your laboratory. This galvanometer is 20 microampere per division sensitivity, that is 20 microampere current is enough to produce one deflection in this one small deflection here in this moving coil galvanometer. You will see that it is a 10 DC moving coil because it can detect direct current. So this is how you have Weston type moving coil galvanometer. Do we have galvanometers of other types also? Definitely we have galvanometers of other types also. This part of moving coil galvanometer may not be important from your syllabus point of view, but to understand ballistic galvanometer it is very much necessary. So here I would like to give you a little insight on the types of galvanometers. So galvanometers can measure either steady current or transient current. To measure steady currents, which you already did in your meter bridge experiment, even the Carey Foster experiment which we performed a few days ago in our laboratory, you got a steady current and you use that galvanometer, Weston type galvanometer, to record or to detect that steady current. But in some cases you have transient current like charging and discharging of a capacitor. So this Weston type galvanometer will not work in that scenario. You need to modify that. And galvanometers are two type. One is moving magnet galvanometer, one is moving coil galvanometer. Moving magnet galvanometer we are not going to study. Let us go to this moving coil galvanometer. So this moving coil galvanometer, the principle already explained. Current is passed through a movable coil placed between poles of a powerful magnet, and the coil swings under the action of the deflecting couple acting on it, and there is the hairspring which provides you a counter torque, and you get a deflection proportional to the applied current. So moving coil galvanometer is of two types. One is that Weston type which we have already shown you here. It is also known as pivoted coil galvanometer, and it is less sensitive but still very much convenient for using in our laboratory like Carey Foster's bridge or meter bridge experiments and different type of bridge type circuits. Now comes your D'Arsonval type galvanometer or suspended coil galvanometer. In this case, again the principle is same. You have a coil and a current will be passed, but here the structure will be completely different. In this case, you will have the galvanometer coil, but it may be wound on a non-conducting material. Your previous case, it might be on a aluminium frame, that Weston type, but here it would be over a non-conducting material, and it may be having a suspension wire which is your made of phosphor bronze. So in this case it will be different than your Western type galvanometer. So what are the differences? Let me explain very briefly. In this case you will have one coil that is there, and there will be another material which will be in the cylindrical form. It was there in your Western type also. That material may be a ferromagnetic material like iron. There I did not mention it. So the coil will be there, and you will have that cylindrical ferromagnetic, maybe iron or something like that, which makes the magnetic field stronger, and it has no role than more than that. And then you have this structure of making the magnetic field radial as it is. What are the differences then? So the difference lies here. Here you have a wire, phosphor bronze wire, connected to a torsion head, and here this rigid support, it is denoted by R, and here this phosphor bronze wire is of rectangular type of cross section, and over that phosphor bronze wire, using glue, a small plane mirror is also attached. And other side of the coil is connected to a spring, and again it is connected to a binding screw. So let us see this diagram to see in a better way. So here comes your diagram. You have that fixed iron core. As I was telling, that fixed iron core, its role is to just increase the magnetic field density, ferromagnetic material. Then you have several turns of wire. Here they have shown aluminum frame over which winding may be non-conducting ivory or some other plastic material for this type of galvanometer which I am discussing. That is your this type, what we called as suspended coil galvanometer. The suspended coil galvanometer may be acting as deadbeat or ballistic. What is deadbeat and what is ballistic we will show you in next class in very detail. But remember that ballistic galvanometer is the galvanometer which is used to detect transient current or charge. So here we are back to the diagram again. So you have the mirror here, then this phosphor bronze wire of rectangular cross section. Making that rectangular cross section makes your tau equals to c theta. Your torque is equal to c theta, where c is your torsional rigidity and its value is less if you make it thin. So that is why this thin and rectangular strip is thin as well as rectangular, means that value of C is less, which in turn gives higher deflection. And here you have the rigid support showing in a much better way. Then this side the spring is not shown, but one connecting screw is also there. So the connection comes from this torsion head wire, external wire, to this bottom here, current source circuit under test. And you will see that how this mirror system works. You have a light source here. This light source falls light on the mirror, that is the light source provides light on the mirror, and the light is reflected on a scale. Here it looks like a curved scale, but in our laboratory we have a flat scale. So this is the construction of your suspended coil galvanometer. This suspended coil galvanometer, which we use in our laboratory, in fact is is ballistic. That is, it is used as ballistic galvanometer. So we do not call it suspended coil galvanometer. We keep calling it as ballistic galvanometer because the features are for ballistic. That is, its use is for ballistic, and there may be or there are suspended coil galvanometers which can be used to take action as deadbeat galvanometer. That is, you will apply a current and there will be a deflection like the Weston type, but in ballistic, as you are measuring charge or you are measuring transient currents, charge flown by transient currents. So in the ballistic galvanometer, coil will swing one, and this swing will be recorded in this lamp and scale arrangement before it comes to rest. So this is how the ballistic galvanometer works, and here another diagram I have. So the second diagram is also similar to the first diagram. Next, you have the lamp and scale arrangement attached to the system, and this is the picture of a ballistic galvanometer. I repeat that the word ballistic galvanometer is written, although it is suspended coil type, but we are using it for measuring charge or transient current. So it is used as ballistic galvanometer. So this is the laboratory ballistic galvanometer, and this laboratory ballistic galvanometer has a mirror here, which you can see. You have a mirror here, then the coil is there. T1 and T2 are two binding screws, then you have two leveling screws. Another split level is also provided for the system to remain exactly vertical. It is very important because the deflections will give us the reading of charge, and you have a torsion head also. So this is moving coil ballistic galvanometer, which we we use in our laboratory. So in this lecture, what we have learned, we will come back to that again. So when we started, we tried to teach you torque acting on a current loop. Then we tried to tell you about Weston type galvanometer, and then we told you a little about ballistic galvanometer. More about ballistic galvanometer will give in next lecture.